So in this part, I just wanted to summarize for you in just a few minutes everything that I hope you need to know for the S matrix. So the first thing that we should not forget is that the S parameters are in general complex numbers. Some of the examples we've seen here actually have given us real numbers, but in general are complex numbers, and they're frequency dependent. For every single network, except for the very simple ones, the S parameters are actually frequency dependent, so you need to know them or measure them or calculate them as a function of frequency. The second thing is that to calculate the S parameters, you must match all ports to their characteristic impedance. This is by definition. You cannot calculate the S parameters if the ending impedance is not equal to the reference impedance of that port. However, once you know them, you can actually, of course, match the network, rather connect the network to any impedance you want, and use the S parameters to find the new response. The other one is that the S parameters are defined as specific reference points. So that means that if you change the reference points and you move them by a specific length, you have to recalculate the S parameters. Our textbook actually gives you those calculations, and you can find them very easily online. I have not covered them in this course. The scattering matrix is also a very generic matrix. We've never placed ourselves on ourselves a restriction of how many ports we can have. We can have as many ports as we want. Some of the other matrices we will see in future lectures, they do have a restriction. For example, the ABCD matrix is defined only for a two-port network. Also, you should remember that most networks that you will see in real life, they will actually have the same reference impedance for all ports. Usually that number is 50 ohms. However, that's not true always. And so the step matrix that we saw, the electrically small step junction that we have seen is actually a good example for that. Finally, the S matrix may give you some trouble if you don't know exactly what the characteristic impedance is, particularly in cases that you work with lumped elements. In that case, you should be using the reference impedance of the entire system that you're designing, and there are easy ways that you can rescale the S parameters for different reference impedances. We will see that in a future lecture. Lastly, something that gives trouble to a lot of us is that the S matrix is by definition linear. However, a lot of the networks that we see are nonlinear. So what do you do is that if you do need to characterize nonlinearities, either you have to make assumptions about weak nonlinearities and then use the S matrix, or you have to use other matrices that are actually made specifically for nonlinear networks, which we're not covering in this class.